Now, in the previous video, we worked on the first order and the problems that you can solve from there. And also we looked at the half-lives. This time around, we want to investigate the effect of temperature on rates of reaction. So for that, we use the Arrhenius equation. The Arrhenius equation is given as the rate constant K is equal to A E EA divided by RT. So that is A and E to the power negative EA divided by RT. So we will try to define whatever we have in here. So EA is the activation energy. The activation energy is just an energy barrier or a hump. So it's an energy barrier that reactants must overcome to become products. So that is activation energy. Then we have A. A is called frequency factor. So frequency factor is just a number of times reactants approach activation barrier. So that is our frequency factor. Then we have an exponential factor that is EA RT. So an exponential factor is just a number. So this one you call it exponential factor. This is just a number between 0 and 1. So what does it do? It represents a fraction of molecules that have to cross the activation barrier. That have to cross the activation barrier. So we have our reaction. We have this activation barrier here. We have all these molecules here, and then we have some 3 molecules or particles. Now, if we add this and this, and then we have this divided by this, we have our exponential factor. Now, you can play around with this equation and make it a natural log. If you make this equation a natural log, it becomes natural log k is equal to minus activation energy over RT plus natural log A. So this one is the Arrhenius equation. So this one is the Arrhenius equation. Now dealing with rate constants. Now, the Arrhenius equation, if you have for two temperatures, and therefore two rate constants, the Arrhenius equation is given as natural log K2 K1 is equal to EA over R 1 over T1 minus 1 over T2. You can play around with the natural log equation that I have given you previously to derive this equation. This equation will be given on your exam, so you just need to know how to use it. So this is the Arrhenius equation for two temperatures and two rate constants. Temperature must always be in Kelvin. So if you have degrees Celsius, you need to change the degrees Celsius to Kelvin. If you use degrees Celsius, definitely you are going to have a wrong answer for this type of problem. Let us see how we can use this Arrhenius equation in an actual problem. Consider the reaction between nitrogen dioxide and carbon monoxide. So the rate constant at 701 Kelvin is measured as 2.57 per molar per second. That is a second order reaction. And that at 895 Kelvin is measured as 567 per molar per second. Find the activation energy of this reaction. So, reaction like this one, the first thing I am going to do is to write the Arrhenius equation. Natural log K2, K1 is equal to the activation energy over R 1 over T1 minus 1 over T2. So as we are already aware, R is universal gas constant, which is 8.314 joules per Kelvin per mole. That's why your temperature should always be in Kelvin, because you are using R that has Kelvin in it. So here we want to find the EA. What are we given? We are given T1. So this is T1. And we are also given T2. We are given the rate constant, K1. We are also given K2. So we have this, we have this. We have this and this. We have this. What we do not have is only this EA. So what we need is just to plug in the numbers. So natural log K2, which is here. Natural log 567 divided by K1, which is 257. This one is equal to the activation energy divided by 8.314. 1 over, what is our T? Our T1 is 701 Kelvin. Minus 1 over, our T2 is 895 Kelvin. So just solving natural log 567 divided by 2.57. This part gives us 5.396. When we play around, 1 over 701 minus 1 over 895 divided by 8.314. So we'll have 3.719 times 10 to the power -5, then EA. So our activation energy let me move step by step. So you want EA to be on its own, so you need to divide both sides by 3.719 times 10 to the power -5. We do the same thing here. 3.719 times 10 to the power -5. So based on this, our activation energy becomes 5.396 divided by 3.719 times 10 to the power negative 5, which is 1.45093 joules. So naturally you want to change it to kilojoules, which is 145 kilojoules. So this is your activation energy. It is not a difficult problem, only that it is cumbersome. So just make sure that you play around with the numbers, you use your calculator properly, and the like. So this is how we solve this problem. A similar problem for the same chemical reaction in the previous problem. Calculate the rate constant at a temperature of 448 Kelvin. So in this case, what you do, you already know your T1 and K1. And you also already know the activation energy, that is 145 kilojoules per mole. Now what you want to determine is K2. So as a solution, I will do a similar thing like we did last time. Natural log K2 minus K1 is equal to activation energy over R 1 over T1 minus 1 over T2. So do not put T2 here. Here we should have T1. So what do we have? We have T1. That one we have. We have T2 here. It's given. We have EA. We have K1. What we need is K2. So we are going to just start putting numbers. As usual, remember R is 8.314 joules Kelvin mole. So here I'll say natural log K2 divided by K1. I'm already given 257. I don't need to put units. Is equal to E. Here you need to change this one. Always change kilojoules to joules. So 145 kilojoule is equal to 145,000 joules. That is what you put in the formula. Do not put kilojoules inside this formula. So we are going to have 145,000 divided by 8.314. 1701 minus 1. T2 is 448. 8. So let's see what we are going to get for this part. So I will put the first parenthesis, then 145000 divided by 8.314, and then close parenthesis. Another open parenthesis, 1 divided by 701 minus 1 divided by 448. Close parenthesis, enter. So for this one, the answer is minus 1405. So this one is your natural log K2 divided by 2.57. So I'll just rewrite this one, K2 divided by 2.57. Let us take note that this is in parentheses. Now you are removing the natural log this side. If you remove natural log this side, this one should be e to the power the whole thing here. So I will say K2 divided by 2.57 is equal to e to the power 14.05. Therefore, K2 is 2.57 parentheses e to the power negative 14.05. So once you do that, you are going to get 2.57 times. Now let me get that e to the power negative 4.1. So times 7.91 times 10 to the power 1, 2, 3, 4, 5, 6, negative 7. So our K will be equal to, so I'll just say the K is equal to 2.03 times 10 to the power negative 2, 3, 4, 6. So the K is 2.03 times 10 to the power negative 6 per mole per second. So the K will have the same units as this other K. So that's how we solve this type of problem. So this is the last problem from this video. The last video will deal with reaction mechanisms. So I will go on to talk about reaction mechanisms, but for now, this is where we are ending.